power on your system, there triggers a series of events that leads to the login prompt. And normally you don't worry about any of that, you just log in and start using your system. However, your Linux system will not always boot correctly. In that situation, having a basic understanding of just how Linux boots the operating system can help you troubleshoot the problem. There are three main steps to the Linux boot process. The firmware starts, performing a power on self-test, and looks for a bootloader from a bootable device. The bootloader runs and determines what kernel program to load. The kernel then loads into memory and starts the background programs required for the system to operate. While on the surface this seems simple, each step has several actions involved. Watching the screen as the system boots, you'll see a lot of informative messages scroll by as the system detects hardware and loads software. Sometimes this information can be hidden, such as in a Ubuntu machine, but you can usually show it by hitting the Shift key or Escape during the boot process. Normally these messages scroll by so fast that you can't see what's happening, but you can use the dmessage command to go back and review the boot time messages for troubleshooting. Most distributions of Linux copy these boot kernel messages to the kernel ring buffer. The kernel ring buffer is a special ring buffer in memory. The buffer is circular and is set to a predetermined size. Old messages are rotated out as new messages are logged. The dmessage command will display the most recent boot messages stored in the kernel ring buffer. The example to your right is of a dmessage on an Ubuntu machine. Most distributions will store boot messages in a log file, usually located in the /var/log folder. And it's usually named something like boot.log, although some systems may have it just /boot. And I'm going to take a quick look at an Ubuntu virtual machine as it starts. Hitting Escape brings up the boot messages. Now, as you saw, all those boot messages went by too fast to see, so we're simply going to open up a terminal and we are going to run sudo dmessage. And this is the boot messages currently contained in the kernel ring buffer. So this is from when I first started my machine just then. So if I was to troubleshoot anything, I would look for like a failed message like here to see what is going on. Now this log file can be found in the var/log folder, so let's change over there real quick. And a quick ls of that machine shows you that I have not only a boot log, but also a boot log 1 and 2 and 3, which are made from all the processes as it's starting up. And now that we know how to see these messages, let's look at what generates them. The built-in firmware helps control how the installed operating system starts. On older systems, this was called the BIOS, Basic Input Output System. On newer systems, the UEFI, or Unified Extensible Firmware Interface, maintains the hardware status and launches the operating system. The BIOS, our Basic Input Output System, was a simple menu interface that allowed you to change how the system found hardware and defined what device the BIOS should use to start the operating system. The problem with BIOS is that it can only read one sector's worth of data from the hard drive into memory to run. That's not enough space for an entire operating system. Because of this, Linux and Windows split the boot process into two parts. First, BIOS runs a bootloader. A bootloader is a small program that initializes the necessary hardware to find and run the full operating system. Often it's found on the same hard drive in another location, but sometimes it's on a separate internal or external storage device. The bootloader usually has a configuration file. You can edit it to change where to find the actual operating system files, or even to produce a menu allowing you to choose multiple operating systems at startup. BIOS must know where to find the bootloader. Most BIOS setups allow you to load the bootloader from an internal or external hard drive, a CD or a DVD, a USB, an ISO file, or a network server using NFS, HTTP, or FTP. If booting from a hard drive, you must designate the hard drive and the partition where the BIOS should load the bootloader. This is done by defining the master boot record. The master boot record is the first sector of the first hard drive partition on the system. There is only one for the computer system. BIOS looks for the MBR and reads the program stored in there in memory. The bootloader must fit in one sector. It must be very small and can't do much. The bootloader mainly points to the location of the actual operating system kernel files stored in a boot sector of a separate partition installed on the system. The kernel boot file has no size limitations. As operating systems became more complex, it was clear that a new boot method was needed. Intel created the UEFI Extensible Firmware Interface in 1998 to address some of the limitations by BIOS. By 2005, the Universal EFI, or UEFI, standard was adopted. Instead of a single boot sector, UEFI specifies a special disk partition, EFI System Partition, or ESP, to store bootloaders. This allows for any size bootloaders, multiple bootloaders, and multiple operating systems. The EFI system partition uses the old Microsoft file allocation table, file systems to store bootloaders. Linux ESP is usually mounted in the boot/FE folder, and the bootloader files are typically stored using the .EFI extension, for example linux.efi. UEFI firmware uses a built-in mini bootloader, often referred to as Boot Manager, that allows you to configure which bootloader to launch. You need to register each individual bootloader file you want to appear at boot time in the boot manager interface. Then you can select the bootloader to run at each system boot. Once the firmware finds and runs the bootloader, the firmware's responsibility in the boot process is done. The next step is all the bootloader's process, and process is a little bit complicated, and we'll cover that next time. So review question time. Question 1. What program does the workstation firmware start at boot time? Is it a bootloader? Is it the file system check program? Is it the Windows operating system? Is it the mount command? Or is it the make init rd program? Take your time, look back through your notes to find the answer. And the answer is a bootloader. Firmware looks for the bootloader to load an operating system. The file system check program is used to check and repair damage to hard drives. The Windows OS starts after a Windows bootloader runs. The mount command in Linux. The mount command is a Linux tool for attaching a partition to the virtual directory. The make init rd program creates an init rd RAM disk used for booting, but not ran during startup. Question 2. Where does the firmware first look for a Linux bootloader program? Is it the /boot/grub folder? Is it the master boot record? Is it the /var/log folder? Is it a boot partition? Or is it the /etc folder? Pause and look back through your notes if you need to. The answer is the master boot record. Firmware looks at the first sector of the first hard drive, otherwise known as the master boot record. The /boot/grub folder and the /var/log folder and the /etc folders do not contain the bootloader program itself. And in a separate boot partition, firmware itself is not able to look at other partitions, only the master boot record itself. Thank you everybody for being patient and following along with me.